In this section, we will learn trigonometry from a right triangle approach. So how do we use right triangles to evaluate trigonometric functions? In this image, there's a triangle that's inscribed in a circle of radius 1. In this triangle, there exists a horizontal length of the triangle of x and a vertical length of y. The sides x and y meet at a right angle, and the point x comma y is a point that's on that circle. Now in this triangle, the radius is 1, and because that triangle is inscribed in the circle, then the circle has a radius of 1, and that is called a unit circle. Now, because the side x and the side y form at a right angle, then we have a right triangle. The trigonometric functions, it turns out, can be defined in terms of this angle, which was t, and the lengths of the sides of that right triangle. And these are the relationships. Always the side across from the 90-degree angle, so this is at the bottom right base in this triangle, is called the hypotenuse. The rest of the sides are all in relationship to a given angle. So in this picture, angle T is identified in the bottom left-hand corner of the triangle, and across or opposite from that angle is the side we call the opposite side. And then the remaining side, which is the one closest to the given angle, we call that the adjacent side. Now keep in mind that if we were interested in the other angle in this triangle, so in the upper right, maybe we call that angle B, the side that's opposite angle B would be a different side than what the side opposite angle T is. So we need to remember that opposite and adjacent can change depending on which angle we're talking about. And we'll look at some more examples of that here in just a minute. So given a right triangle with an acute angle of t, the first three trigonometric functions are, for the sine of the angle is equal to the side opposite that angle over the hypotenuse. Remember, the hypotenuse is not going to change. It's always across from the right angle. For cosine, the cosine of an angle is equal to the adjacent side from that angle over the hypotenuse, and the tangent of the angle is equal to the side opposite the angle divided by the side adjacent to the angle. Now you'll notice that some of these letters are in red, and that's because there's a mnemonic device for remembering these relationships. And you may have heard this before because you do see it a lot. People will say things like SOHCAHTOA. And what SOHCAHTOA says is that the S stands for sine, the C stands for cosine, and the T stands for tangent. And then the letters that follow, for example, for sine, the O and the H, those represent the ratios for numerator and denominator. For cosine, the A and the H represent adjacent and hypotenuse, also the ratio for cosine. And then for tangent, the TOA, O and the A represent opposite and adjacent. So just a mnemonic device that might help you in the beginning to remember these relationships. So when working with right triangles, the same rules apply regardless of the orientation of the triangle. On the last slide, we saw a triangle with the right angle down at the bottom right. If we rotate that triangle around, and so now the right triangle is in the upper left, the hypotenuse is still going to be the side that it's across from. However, if we let the other two angles be called alpha and beta, for example, let's take a look at alpha. Alpha, the side across from that is opposite. So that's the side that's opposite alpha. But if we look at beta, for beta, the side that's closest to beta is adjacent. So in this situation, that side is not always opposite, is not always adjacent. It depends on the angle that we're referring to. So although the hypotenuse will not change, the side opposite one acute angle is the side adjacent to the other acute angle and vice versa. So we have to be careful about that. So let's take a look at an example. In this right triangle, we have a hypotenuse of length 5, and we have two sides that are length 3 and 4. And the instructions ask us to do two things. First, find the sine of alpha. So let's do that. The sine of alpha. The sine of alpha. Well, we know that sine is opposite over hypotenuse. All right, so if I identify alpha in the bottom left of that triangle, the side that's opposite alpha is 4. And of course, the hypotenuse never changes. That's always going to be 5. That's the side that's across from the right angle. Now let's do cosine. And cosine said the cosine of beta. All right, and beta is in the right-hand corner of the triangle. Let me just circle that. And the ratio for cosine is adjacent over hypotenuse. All right, so the side that is adjacent, that's the closest side to angle beta, not including the hypotenuse, right? So the hypotenuse is going to be 5. That's not going to change. 4 would be that closest side. One thing I always do is if I have a hard time identifying the adjacent, I know I can identify the hypotenuse. And for me, the side that's opposite the angle always feels really clear. And so that leaves me with the adjacent side. So the sine of alpha is 4/5, and the cosine of beta is also 4/5. So is that a coincidence that they equal each other? What is the relationship between alpha and beta? Well, it is a right triangle, so the only relationship I can see right off the bat is that alpha plus beta, I don't necessarily know what each one of them equals, but I know that their sum must be 90 degrees. And that's because the sum of the angles in a triangle is 180 degrees. And if I already have the right angle at 90 degrees, then alpha plus beta has to be 90 degrees. We say when two angles add to 90 degrees that they are complementary angles. Okay, so let's just keep that in mind as we move forward. So let's try another example where we're asked to evaluate a trigonometric function of a right triangle. Part A says, given the triangle below, find the value of the sine of angle T. Now this triangle is a right triangle, and the side that's across from that 90-degree angle has a length of 25. The other two sides have a length of 7 and 24, and angle T is in the bottom right-hand corner. So we're being asked to find the sine of angle T. The sine of an angle is equal to the ratio of the side opposite the angle. So I'm going to say opposite, in this case, angle T, over the hypotenuse. Over the hypotenuse. And I don't have to say hypotenuse of an angle because the hypotenuse does not change. In fact, I can just go right to filling that out. We said that the hypotenuse was 25, so that's going to be my denominator. And now all we have to do is determine which side is opposite angle T. And the side across or opposite angle T looks like it has a length of 7. So we're going to say that the sine of angle T is equal to 7 over 25. Part B, given the triangle below, find the value of the cosine of angle T. Now this triangle has rotated from the triangle that we saw in part A, Now the 90-degree angle is in the upper right-hand corner, and the side that's opposite that, the hypotenuse, has a length of 65. Angle T is in the upper left-hand corner, and the two remaining sides have a length of 56 and 33. So what is the cosine of that angle T in the upper left-hand corner? Well, that ratio is the side adjacent angle T, and the denominator is the hypotenuse. Now, what is that hypotenuse? We said that it was length 65, and the side that's adjacent to angle T, we know that opposite across from angle T is 33. We know that 65 is the hypotenuse, so that leaves the side closest to angle T as 56. So we can say that the cosine of angle T is equal to 56 over 65. Here's what we know so far. We know that the sine of an angle is equal to the side opposite that angle over the hypotenuse of the right triangle. We know that the cosine of an angle is equal to the side adjacent that angle over the hypotenuse of the right triangle. We know that the tangent of an angle is equal to the side opposite the angle over the side adjacent that angle. So in this example, we're asked to evaluate the 6 trigonometric functions of angle T. Now this triangle is the same triangle that we saw in part B on the previous slide. It has a hypotenuse of length 65. It has two remaining sides of length 56 and 33, and angle T is in the upper left-hand corner. And what we said was that the cosine of angle T was equal to 56 over 65. And that was because in relation to angle T, 56 was the adjacent side. All right, but now let's fill in the rest of them. Sine of T is equal to the side opposite angle T, so 33, also over that hypotenuse of 65. The tangent of T is equal to opposite T, which we just said was 33, but the denominator is going to be the side adjacent to angle T, which is 56. You might have already noticed, but the tangent is the only one that doesn't rely on the hypotenuse. So something to keep in mind as we move forward. Now, what are the cosecant, secant, and cotangent relationships? Well, that's where the idea of reciprocal functions comes into play. We know that the sine and the cosecant are reciprocal functions, and so the cosecant is going to be, instead of sine, which was opposite over hypotenuse, cosecant is going to be hypotenuse over opposite. And if I've already determined what the sine is, which I have, all that I have to do is reverse the numerator and the denominator. So the cosecant of angle T is equal to 65 over 33. And I bet you can figure out the rest of these. Secant of angle T is the reciprocal of the cosine function. The cosine of angle T was 56 over 65, so the secant is going to be 65 over 56. And then lastly, cotangent. The cotangent of angle T is going to be the reciprocal of the tangent function. The tangent of angle T was 33 over 56, so the cotangent of angle T is 56 over 33.